We are diving into a paper that answers a really fundamental question in AI right now. How much 3D do video foundation models encode? The authors took some of the biggest video generation models out there. We're talking models trained only on massive amounts of flat 2D video. And what they found is pretty staggering.
It is. They discovered that these models have developed this incredibly strong and completely emergent understanding of the 3D world. Nobody programmed this in, it just learned it.
Yeah, and the key insight, which is a big deal for computer vision, is that these video foundation models, or VidFMs, like WAN2.1 14b, are so good that their features can actually outperform expert models that were explicitly trained for 3D reconstruction.
Right, they beat the specialist. And not on some easy task, but on really challenging out-of-domain scenes.
And for anyone listening who's an engineer, this paper gives you a roadmap. It pinpoints exactly where these powerful 3D features are inside the models. It's consistently in the mid-network layers and in those early, but not the very first denoising steps.
It basically confirms that the whole push for making realistic video is, sort of by accident, solving this huge, long-standing problem of learning 3D representations at scale.
Okay, so let's unpack that, because it's a huge claim. Recovering 3D structure from 2D has been, the holy grail of computer vision for decades.
A huge bottleneck for decades.
Yeah. So what was the bottleneck?
It always came down to data. Getting high-quality, ground-truth 3D data is just incredibly hard and expensive. You need LiDAR, special scanners.
And it's not scalable.
Not at all. And you end up with these bespoke models that work great in the lab but fall apart in the real world.
Meanwhile, the amount of 2D video data is just a fire hose.
Exactly. And that's the core hypothesis of this paper, which is so simple and elegant. It's that since every video is just a 2D projection of a real 3D world, a model trained on enough of it has to learn the underlying physics and geometry to make the video look real.
It has to. To generate a camera moving around a car, it has to implicitly know what the back of the car looks like. It has to understand perspective.
It has to understand 3D. And we've seen other work try to, bolt on 3D controls to these models. But this paper asks a different question.
Is the knowledge already in there, in the base model?
Exactly. Is it inherent? So they designed this model-agnostic probe to find out. And they set a really high bar for it.
Okay, so let's get into the methodology. How do you peek inside the brain of a frozen multi-billion parameter model?
So they use a technique that's pretty similar to DIFT, or diffusion features. You pick a point in the denoising process, say time step tau, you add noise, you run one denoising step forward.
Just one step.
Just one. And then you read the hidden activations from an internal layer. That gives you a feature vector, f sub t, which is like a snapshot of the model's geometric reasoning at that moment.
And the probe itself has to be simple, right? It can't be some giant network that's just learning 3D on its own.
Absolutely. That's the critical constraint. The probe is a very shallow, VGGT-like transformer. It's lightweight. It takes in 4 frames, a reference frame, and 3 others, and just mixes those features a little bit.
So that small bit of temporal mixing helps it see the multi-view information.
Right, but the heavy lifting is already done. The features are frozen. And this little probe has 3 jobs, 3 readout heads. It has to predict dense 3D point maps, dense depth maps, and the camera pose.
All from those frozen features. So if the probe does a good job, it proves the knowledge was in the features to begin with.
That's the logic. It's a direct measurement of what the base model already knows.
So let's talk about the testing grounds. The datasets here were chosen very deliberately.
They used 2. First, CO3DV2. You can think of this as the in-domain test. It's mostly clean, object-centric videos, like an object spinning on a turntable.
The kind of thing you'd expect a 3D model to do well on?
Exactly. And then they use DL3DV. This is the hard one. It's full of large, cluttered, messy, real-world scenes. It's a true test of generalization.
And the metrics were tough, especially for that global consistency part.
Yes. For point maps and depth, they used a standard L2 error. But for camera pose, they used something called AUC at 30.
Which is really unforgiving.
It is. You only get credit if your rotation error and your translation error are both below the threshold. It means you have to know not just what the scene looks like, but where you are in the scene very accurately.
Okay, and this is where the story gets really interesting. They benchmarked the big video models, WAN and OpenSora, against controls like DynoV2 and a dedicated 3D expert, Fast3R.
So on the easy dataset, CO3DV2, the results are what you'd expect. The expert, Fast3R, wins. It was probably trained on similar data.
Right. It scores a .769 on AUC at 30, and 1 is close behind at .736. Competitive, but the expert is still the expert.
But then you get to DL3DV, the messy, out-of-domain data, and the whole narrative just flips.
It flicks completely. Why does that happen? Why is that data set the crucible where the video models pull ahead?
It's all about generalization. Fast 3R is powerful, but its knowledge is specialized. The video models, because they had to learn to generate such a vast variety of scenes just to make pixels look right, they ended up learning a much more general, robust model of the world.
And the numbers back that up, right?
Oh, absolutely. On DL3DV, WAN2.114b beats Fast 3R on every single metric. Point error is 1.051 for WAN versus 1.379 for the expert. That's a huge gap.
Wow.
The depth error is even bigger. 0.323 for WAN, 0.514 for Fast 3R. And even on that tough AUC at 30 metric, WAN wins. 0.660, 0.637.
That's the smoking gun right there. A model trained only to make videos is better at general-purpose 3D understanding than a model built for it.
You can see it in the pictures. The qualitative results are so clear. On the cluttered scenes where the image model, DNF2, just catastrophically fails, WAN produces these sharp, coherent 3D reconstructions.
Incredible. So the authors then tried to figure out why this is happening. Let's talk about the ablation, starting with the big one, temporal reasoning.
This is fundamental. They compared DNF2, which sees each frame in isolation, to VJPA, which is a video model that understands time.
And the difference is night and day.
It's a death sentence for the image model on global tasks. On the hard DL3DV data, DynaV2's AUC score just plummets to 0.245, while VJPA is up at 0.558.
So seeing things over time is non-negotiable for building a 3D world model.
Absolutely indispensable. You need that flow of information to understand how the camera's moving and how the scene is structured.
Okay, what about the next factor? 3D fine-tuning. Intuitively, you'd think this would always help, right?
You would. And they looked at a model called Aether, which was fine-tuned on 3D objectives. And on the DL3DV dataset, it did improve over its base model.
Which makes sense. That was probably similar to its fine-tuning data.
Exactly. But here's the catch. On the object-centric CO3DV2 data, Aether was actually a little bit worse than its base model.
So specializing it for one domain hurt its generalization in another.
That's the trade-off. You might be sacrificing this incredibly powerful general knowledge that the model learned from video, all for a small gain on a specific type of data.
Okay, and the last factor, model scaling. Bigger is always better, right?
Well, not always. It's more nuanced. When they scaled the WAN model from 1.3 billion parameters up to 14 billion, the 3D error dropped by 23%. A clear win for scale.
But not for the other model family.
Right. When they scaled Cog-Video X from 2 to 5 billion, the 3D awareness actually got slightly worse.
So it's not just about parameter count.
No. The authors think the key difference was probably the data. The larger WAN model likely saw more high-quality, high-resolution video. It reinforces this idea that to get good geometry out, you need to train on data that has good geometry in it. Data quality is king.
Okay, so we know the features are great. We know why. Now for the practical part, where do you find them? Where are these 3D-aware features concentrated?
This is one of the most useful findings in the paper. The location is incredibly consistent across all the diffusion models they tested. It's always in the mid-network layers.
In the middle layers. And what about the time step?
An early but not first denoising time step.
Give us the intuition for that. Why the middle and why not the very beginning?
So if you look at the final layers of the network, they're becoming hyper-specialized on just painting pixels. They're making the final RGB image look good, and they actually suppress the abstract 3D structure to do that.
And if you look too early,
it's mostly just noise. The model hasn't formed any high-level concepts yet. And for the time step, the very first steps are too noisy. But you want to be early enough that the model is still thinking about structure and not just color. So that mid-layer, early-ish step is the sweet spot.
That makes a lot of sense. It's the point of maximum geometric reasoning.
Exactly. Before he gets distracted by making things look pretty.
And they use this finding to do a direct application test, right? Against the standard Dino features.
Yes, this is the kicker for anyone building applications. They made a model called VidFM-VGGT using these WAN features and compared it to a standard VGGT that uses Dino features.
And the VidFM model was way better.
Substantially better on both datasets. But the really staggering part was the data efficiency.
Right. This is the big takeaway.
The VidFM-based model, trained on less than 10% of the available 3D data, consistently outperformed the Dino-based model that was trained on 100% of the data.
Let me just repeat that. Better performance with 1/10 of the data.
1/10. So if you're in a field where 3D data is scarce or expensive, robotics, medicine, whatever, you are far better off using features from a big video model than trying to collect more 3D data.
So before we wrap, there's a really important nuance they pointed out. They challenged a very common metric in computer vision.
Right, multi-view consistency. The idea that if features for the same 3D point match up well across different views, the model must have good 3D understanding.
Which sounds logical.
It sounds logical, but it's not the whole story. They showed that a model like DynaV2 can have excellent cross-view consistency, low error, but still be terrible at the actual 3D probe task.
So how can that be? The features match, but the 3D is wrong.
It seems like you can learn to match local features really well without ever building a globally consistent 3D representation of the whole scene. The parts match, but the whole is incoherent.
And for the diffusion models, their raw features might look less consistent because of all the noise in the process, even though the underlying 3D knowledge is actually much stronger.
Exactly. So the takeaway for the research community is huge. Cross-view similarity is not a good enough proxy for 3D awareness. You need to do a direct probe like they did.
So what's the final message for you, for the technical listener? It seems to be that large-scale video training is creating these emergent world simulators.
It is. And if these models already contain this incredibly high-quality, actionable 3D information, maybe the next big breakthrough isn't just making better videos. Maybe it's about efficiently extracting that 3D world model.
Using it as a universal simulator for robotics or AR.
Right. And that leaves us with a really provocative question. Given the crazy data efficiency we just talked about, how much time and money could we save in 3D research by just treating these big video models as our starting point, as pre-trained world models?
The foundation seems to be built already. The challenge now isn't about generating pixels, it's about extracting the geometry that lies beneath.